Good evening and welcome everyone to this talk. I am Chinmay Soman, founding engineer in StarTree. I also lead the product org here, and definitely amazing to be back at my previous employer. So thank you for having me. Today I'll be talking about what's the secret sauce behind Apache Pinot. What makes it so fast? So we'll go through the architectural decisions that led us to this place. But before, why do we care? We all know, for OLTP databases, speed, throughput, and latency makes that's very important. But why does it matter for OLAP use cases, right? Ujjwala sort of touched upon this already, but in case you're still not convinced, here's some more examples. This is the classic one from LinkedIn. And so LinkedIn provides a lot of analytics and insights to their users. So things like talent insights, the classic who viewed my profile, and then also the content relevance for your newsfeed. So they basically analyze user behavior and then ensure that you're seeing the latest, most relevant content on your feed. And most of these applications behind the scenes are running OLAP queries, something like this. Right? So it has some aggregations, filter, group by, order by, maybe even joins. So the query themselves are not that complicated, as you can imagine. But the scale of things is what makes it very challenging. Right? So LinkedIn has 930 million plus users from my today's Google search. Has obviously to support these user-facing insights. Any active member on LinkedIn, when they are browsing through the site, they're firing these queries on the backend. So we're talking about tens of thousands of QPS, and the main part here is the latency SLA, which it has to be less than 100 milliseconds for P99. This is another great example from Stripe. I'm actually stealing this slide right from Lakshmi, who's sitting right here. So thank you for that. But Stripe has a real-time platform which is used for building all kinds of dashboards that they expose to their merchant partners, internal developers, and so on. Also used for other things, as Lakshmi mentioned, billing analytics, developer analytics, and so on. And again, the scale of things and the latency SLA is quite stringent, right? So talking about 20,000 plus QPS, and then even stringent SLA here, in this case, less than 50 millisecond P99. And of course, I think Ujjwal already showed this, but here's the Uber Eats example where this dashboard is shown to, again, my Google search says it's 900,000 restaurant partners as of today. Every time they log into this dashboard, they get a view of the order status, missed orders, and financial stats, and so on. So you're talking about lots of QPS, and again, the latency here has to be sub-second and in a predictable manner. So all these use cases and many more is being powered by Apache Pinot today. For those who are new to Pinot, it's a distributed OLAP database coming out of LinkedIn that can ingest data from all these different data sources you see on the left, like Kafka, S3, GCS, and then make it available for serving and power a wide range of use cases, as we saw before. The last few years, we have seen a massive adoption amongst different companies across the globe, and in different segments, right? So you have prominent names like Walmart, Target, 7-Eleven on the retail sector, Citibank, Stripe, VPay, and so on, and the financial services industry. Food and logistics is actually where I think Pinot is a segment winner. Every major company in this segment across the globe has actually adopted Pinot, which is monumental, and so on. So it's quite popular across all these segments. Also quite a vibrant community, 3,900 plus Slack members and counting, and lots of Docker downloads, which is great. All right, so for the rest of the talk, the structure is the following. Right? We'll go through the high-level architecture of Pinot just to understand the basics of query processing and what are we trying to even optimize. And then look at optimizations applied to different layers in the stack to get the speed and the scale that Pinot can support. All right, so as I mentioned, Pino is a database, right? The table in Pino is a logical concept composed of what we call as these Pino segments. Right? So Pino segment is a subset of your data. If you sort of peek into it, it's actually the data organized in a columnar fashion, along with any of the indexes that you've specified on your table. So in a Pino cluster, all these segments are sprayed across the available Pino servers. So Pino server is a component that locally manages and processes the segments and then generates the result. We also have the Pino controller. That's the brain of the whole cluster, takes care of membership, coordination, segment assignment, and so on. And finally, the Pino broker. So that's responsible for query processing. Every time it gets a query, it does a scatter gather to generate a result. What that means is it will identify which servers do I need to send this query to, right? Those servers in turn will locally process the query, generate an intermediate response, and then broker will collect all these responses, do a final aggregation, and then return the result. So as you can see, it's a good scale-out design. So if you want to handle more data, more QPS, you just keep adding more components, and then it horizontally scales quite well. One thing to note is without any optimizations, the broker will try to process every single segment that's available in that table. And this is key to understand, right? So that means in this case, it's going to, for any query, it's going to try to process all 12 segments here. So the whole purpose of optimization is to minimize the work done per query, right? What that means is minimize the number of segments that we need to process, and also minimize the number of servers that we need to process to answer a given query. And then, as you can expect, these optimizations are applied at different levels in the cluster. So there's some applied at the broker layer, there's some optimizations at the server layer, and then finally also the biggest optimization is actually at the segment level. So in the next few slides, we'll go through each one of these optimization in detail, starting with broker, right? So as I mentioned, broker will try to process everything without any hints or any optimization applied. So there are a few things that we can do to simplify this at the broker layer. One is time-based pruning, right? So let's assume the broker gets a query like this. Select some aggregation for a given time range, right? So Pino table, there's a time column that you can define in your schema. And for that time column, I want to generate an aggregation for a specific time range, right? Naturally, all segments here don't matter, right? We want to select only those segments that fall in the time range. So in this case, the broker can look at the segment metadata, which includes things like start time and end time of each segment, right? And just by looking at this, it can filter out most of the segments that fall outside of this range and only focus on the ones that are relevant. So for example, let's say only 1 and 3 are relevant here. So broker can now, without looking at the data, it can only send the query to server 1. So from a fan out of 4, almost like 75% reduction in the work that we are doing to answer this query.
So are segments updated in place?
The question was, are segments updated in place? Well, the segments are immutable. Right, so once you generate a segment, the indexes and the data are locked in. There is a way to update it in the form of upserts. So if you have a primary key on your table, you can mutate that data, but that's handled in a different manner. So the segment themselves are immutable, but we can still provide this functionality. But in this case, the segment metadata is basically locked in if that's what you were getting at. So that piece is static. Another thing we could do is partition pruning, right? This works when your data can be partitioned on a certain column. Right? So for example, let's assume this is a query you get, select count star, where user ID is whatever. And the assumption here is you have a lot of queries that are trying to filter on user ID column. In this case, you could partition your data on user ID and specify that in the Pino table config. So Pino knows the data is partitioned on user ID. In this case, again, when a query like this comes in, it can look at the segment metadata, which includes the partition information, and then filter out most of the partitions that don't have whatever partition 1, 2, 3, 4 maps to. It can filter that out, and again, focus on only a few segments instead of all the segments. A third thing that you can do at the broker layer is to reduce the fan out. Right, so the fan out is basically how many servers you're trying to reach for answering a query. So another concept that Pino has is called as replica groups. So this is not really a broker concept. This is a way to sort of assign segments amongst the available servers. So replica group is basically a collection of servers that contains a full copy of the segments in the table. So you could take, you can define a replication factor of 2. One group contains all the segments, the other group contains all the replicas. So this is the same segment is in both the groups. So what this allows the broker to do is to query any one of these replica groups. So suddenly from a fan out of 4, now you only need a fan out of 2. You reduce it by half, basically. So obviously this, is good for the latency, but also improves throughput, and which is important for all the use cases we saw before.
So reducing fan out also has impact on the scalability, right? We tend to limit scalability also by reducing fan out.
Yeah, good question. The question was, we are reducing the fan out, but we're also reducing the question is, does this reduce scalability or not? Well, you can always increase the number of servers within a replica group, right? So that still remains. All you're doing is, instead of spraying segments randomly across the servers, you're saying limit it to like these servers, but you can still have 4 or 8 or 16 servers within a replica group.
This will also increase the fan out, right?
Yes, so it's a fine balance between obviously data scalability and replica group, but then you can apply the other optimizations which will help. All right, so with some of these optimizations, we have reduced from like 12 segments to, let's assume, this is a hypothetical example, but we basically reduce the number of segments by doing stuff only at the broker layer. So we haven't touched the data so far. So now let's look at what happens in a server. Right? So in some cases, you can only prune the segments so much at the broker layer. So we can do further optimization at the Pino server. Right? So let's assume you're getting a query like this on a different column. You're filtering on player ID, for which you don't have the previous optimizations. In this case, we can define a Bloom filter on this particular column. Right? So each of these servers will have a Bloom filter on player ID. And when it gets the query, it can use the Bloom filter to again filter out segments that don't contain that particular value of player ID. Right? So in this case, it will, without looking at the data, we still haven't touched the data so far, we can eliminate segment 3 and just focus on segment 1. Right? So this enhances, again, it further cuts down the number of segments you need to process for answering the query. All right, so at this point, after this, we now need to do the segment processing. We can't obviously avoid the hard work. So let's see what happens within a segment. Right? As I mentioned before, segment is a subset of your data. So assume these are some subset of your input rows. When you create a segment from these rows, basically it takes the data and organizes it in a columnar fashion. Right? So in this example, all the values of country are stored together. Same thing for the browser and so on. This already is pretty optimal for OLAP queries. Right? So for example, if you want to do an aggregation and filter on some specific country, right? Instead of having to scan all the rows in a typical row store, you only need to look at one column, which is the country column. Right? So this reduces how much data you need to scan from the disk, how much data needs to be brought in memory, and obviously great for the query latency. Right? This improves latency and throughput indirectly. But the other thing you could do is add an index for that column, right? So in this case, we can add an index on country, right? So instead of scanning even like one column, we don't have to scan at all. We can just look up which document IDs or which rows have that particular value and do a quick aggregation. And Pino, this is the best part of Pino, right? It comes out of the box with a wide range of indexes, which can accelerate different kinds of use cases. So you have inverted index and sorted index, which works on the numerical values, and you can do things like look up pretty fast. So if you're going to filter on some column with an equal to clause, these two indexes work great. If you have a range query, so if you have where hits is greater than 11, something like that, you can use a range index in that case. For semi-structured data, you could actually configure JSON index. So imagine one of your columns is actually just JSON data. You can configure JSON index on it and do JSON match queries, which will be much faster than defining like a UDF for JSON. Similarly, you could define a text index for if you have just a string column, you want to do text search on this. This could be prefix, suffix, or regex, whatever you want to do, right? The text index will accelerate those kind of queries. And then geo index is actually, thank you to Uber for contributing, but for any sort of geo data, you could use this index for accelerating point and polygon or distance kind of queries. So these were all these indexes accelerate the filtering phase of a query. So whenever you're doing a where clause, these indexes will help in minimizing the number of records you need to scan for processing the query. The other thing available in Pino are things to accelerate the aggregation function themselves. Right? So if you're trying to do approximate functions, there's theta sketches, HLL, and tdigest, which is available today for fast aggregation. And then last but not the least is our favorite StarTree index, which does both things. It can actually help in the filtering part as well as aggregation part. The way it works is for a given set of dimensions, it will pre-compute some aggregation function across all kinds of combination of those dimensions. So whenever a query comes in, it can very quickly look up an aggregation, the pre-computed value without even having to do much scans. The why indexes matter in these kind of databases, right? So when we compare this versus other databases that don't have indexes, this chart will explain the key difference, right? When your data size is small, right? If you're a few nodes, most databases will give you great latency and throughput. But as you keep growing, as you keep organically adding more data, adding more QPS or concurrency, this is the pattern we see, right? Without indexes, you're bound by how much data you have to scan for a given query. That grows linearly with the amount of data. With Pino, on the other hand, the goal is to sort of keep this curve as flat as possible, right? So even if the data grows, workload grows, we minimize the number of things that we need to process using indexes and get predictable latency even with increased growth. These are some of the benchmarks we've done internally on the different with and without the index, right? So as you can see in some of these cases, there's many orders of magnitude difference, especially visible in StarTree index. This is one of the blogs we posted from StarTree side, where this is one of a real world use case where the latency went down from like 592 millisecond P99 to 25 millisecond. Not only that also helps you get a huge increase in throughput. The max throughput before was about 28. I was like 2 orders of magnitude higher with StarTree index.
What's the cost of an index? For the same data, we can have multiple indexes, and now when we are ingesting data into that table, we'll have to update all these indexes, right?
So the question is, what is the cost of an index, and do we need to update an index as new data is ingested? No. So The cost of an index is there, obviously. Like every time you add a new index, there is more storage footprint, there's more memory that's being utilized. But when a segment is committed, the indexes are basically final in that, right? You can regenerate the segment, but once it's generated, you don't have to touch it again. Obviously, this for a new consuming segment, this matters. Some of the indexes are only generated when it's committed, not during real-time ingestion. Yeah.
I'm just curious, is it dynamic indexing or it has some frequency?
Sorry, can you?
How does the indexing happen?
Question is how?
Dynamic, real-time?
Yeah. So question was, how does indexing happen? So let's say you define an inverted index, right? For real-time ingestion, like it will be as your data is being ingested, it will keep updating the dictionary and the index in memory. And when you commit it, you flush the columnar data along with the indexes on disk, and after that it doesn't change. So yes, the indexes are real-time. So for any fresh data, it will actually leverage the indexes, and for at least for inverted index. All right. So through this, through the slides, we saw that Pino is indeed powering many mission critical use cases across different companies. And it was designed from the ground up for like supporting high QPS, low latency in a predictable manner. So it is able to achieve the strict SLA across all these companies. It is an indexing powerhouse, so it can, it's a wide range of indexes available for accelerating different kinds of use cases. We're trying to minimize the work done per query. That's really the design principle across the board. And also it's a scale-out architecture. So after a certain point, you've optimized as much as possible. You can always add more resources and horizontally scale your workload. And that's it. So, Pino is indeed fast.
I'm Ankit. I'm happy to present some of the recent work that we did to enable Pino joins at scale for a production use case internally. So as you might know, like joins is a recent feature that was added to Pino. Before that, we didn't support joins. And yeah, it was a journey to make it happen. We launched it for a big use case internally recently. And this talk will just cover about like how our journey was and where we go from here. So just for context, this was a big internal marketing use case that we had. For those of you who know, like there is a term called cohorting. Like I didn't know about this before the use case, but that basically means that you have a set of users. So let's say all Uber users, and you have a set of attributes for them. So let's say you're looking at users who have taken a trip in the last 60 days or so, who are a part of Uber One membership, which you should join, by the way. And who are in particular city ID, and you want to send a particular kind of marketing campaign to them, then you are interested in like getting the user UIDs which match those particular traits. And this is like a common thing which is used like almost everywhere. For Uber, like the issue was that we relied on a proprietary database before, and that database was costly to say the least. And we were like trying to figure out how to move away from it for quite a lot of years, to the point that I think when we ran out of all options and Pino announced that there's going to be a multistage engine in Pino, then we were like, let's try this out and let's invest a lot of resources on this. So that's what we did last year. We started working on it, and the key requirement for the use case was that we needed to do distributed joins. And obviously you want low latency because everyone wants low latency. And another thing which was a key blocker for us from migrating to other technologies that we have internally was that we wanted real-time data updates. And we're talking about like 1 million writes per second or something like that. So there's a lot of writes per second that you want to support, and you cannot afford to like have a very high lag in the writes. So yeah, those were the requirements. The scale was high. We didn't have any technologies internally. Pino announced multistage engine. We thought let's try it out. And yeah, I think there were like a lot of reasons like why we wanted to do this, but obviously the biggest one that comes out is that the dollar savings was like really, really huge. We have a Pinot team at Uber, so like having the same platform for everyone like means that you have a consistent support across all the technologies. So, but I'll talk about that in the end. Yeah, and just for context, like this is how things used to look like, and they still look like this, but Pino could only support stuff like this. So we had scatter gather kind of queries. So your broker is where your queries get submitted to. And the servers are where the data is. So the broker only does like query processing, query planning, and in the end, it also does a reduced step from all the servers. But this is what we had before. The servers would have the data, and let's say you have a query like select count star, city ID, blah, blah, blah. These will be run in the servers, and the counts and the grouping sets that you get out of the server, they are again reduced back in the broker, so you can return the right result back to the user. So this is what we had before, and with this design, you cannot support join queries. So there needed to be like some redesign of this system, and which is what the multistage engine did. And with the multistage engine, you can do stuff like this. So this is a query plan. Previously, I was just showing the server topology, but in the query plan, you can have any sort of complex query which is doing any SQL-y expressible stuff. So for example, in this case, this is like similar to the use cases that we have internally. So we have a riders table which has all the riders that are there registered at Uber. With certain attributes like device OS, last trip they took, and other attributes, and we want to do cohorting on this. There is another table which is like the audiences table. So users are also allowed to create certain kind of audiences which might not fit the attributes that we have in this table, and they can import that using some tooling that we have internally. So someone could go to the UI and say, okay, I want this. My users are sitting in this particular table in Hive, and I want them to be ingested into Pino. There is a streamlined process for it. We have a dedicated platform for it. That data ends up there in Pino, and once it ends up in Pino, now they want to see like, I want to target users who match these particular traits and who are part of this particular audience UID that I ingested in the past. So, yeah, it leads to queries like this. This is like an example. There is a bunch more complex queries, but the issue with the previous design was that we couldn't do something like this because this requires data shuffling. Like you cannot have a single server doing everything and just returning it back to the broker. Like you could implement it in certain cases and it would work in certain cases and blah, blah, blah. But in the end, you want to do it properly. You cannot be just like, oh, it works for this partitioned use case and it doesn't work for some other use case and for some other query pattern. So yeah, so the multistage engine fixed all of these issues, and this is what we were going for. This was our goal to enable. And just for like the scale numbers, I think you can take your time to like go through it, but we had a bunch of writes per second. We had really wide columns, which is not something we have had at this scale before. So this was also like something new to look at, like hundreds of columns in a table which is like doing hundreds of thousands of messages per second. And the tables themselves were like terabytes large. We have had terabytes large tables, but not like joins was obviously the first thing that we did. So this was like a new experiment. The joins were also large, like you have billion cross hundreds of million kind of joins. QPS was low, but the thing about like when you're looking at long-lived queries, I don't think like QPS is a good metric that you should track, but when you have flexibility on the latency of the query, I think you should be looking at from an engineer's perspective, you should be looking at the concurrency of the queries, because that is where you will probably saturate. Like if let's say you have 5 QPS and the queries are taking 2 minutes, in 2 minutes you'll have like a bunch of queries which will be running like, which will probably like outnumber your vCores per server. So you have to look at concurrency at that point and not exactly QPS. But yeah, QPS is a bit low, but it's consistent and the concurrency can exceed the number of vCores that we have. And we have super complex queries. The issue is that we have opened this to users, and users want to do whatever. So they will have like 10, 20 different audiences. They'll be like, I want users in this audience but not in this audience, and in this audience but not in that audience. And that immediately becomes like a query which has like 10 plus joins, which leads to 20 plus stages. And it leads to like all sorts of weird patterns and like scalability and other issues that you may expect to come. So yeah, obviously that now that I'm giving the talk, we know that it works, but I'm just like setting the context, like why it was challenging to get it to work. But yeah, so, and another thing was that we wanted to support streaming like a lot of rows back to the user. And this was again something that we haven't done conventionally in the past. So in this case, like the requirement was that they want to stream billions of rows back to the user, because the users are interested in give me the user UID so I can run my marketing campaign. So just returning counts wasn't going to cut it here. So that was also something that added to the complexity. And yeah, the queries are dynamically generated. There's a very neat UI which like allows you to do like, I want users in here which are in this custom audience and will have these attributes. So the users are not writing the queries. The users are dealing with a very friendly interface. And the queries are dynamically generated. So which means like usually what happens with Pino is that the queries are hard coded in your backend service. So it makes it easy to predict the query pattern and the query load. But with this kind of pattern, people can generate any sort of joins. So 1 hour you won't have anything. The next hour someone is running like billion cross 100 millions of joins, and you'll have a different performance altogether. So that was also one thing which added to the challenge of this. Apart from the fact that master was like Pino master was like progressing at like 50 commits per week, and so that was also a bit of a challenge. But yeah, going back to the journey, so I'm starting with January because that is when let's say the heat turned on. Like if you thought this was hot, you don't know me in January. But the heat was really on because we enabled shadow traffic from our customer. And we essentially had 0% reliability. Everything was going down. Every 2 hours, the servers will crash. Memory was full. Ingestion lag was like 1 day. And the table retention was 2 days. So yeah, it was not a good time. And essentially, like the story was that we went on vacation like in December, as I think everyone does. And I came back and I looked at my Grafana dashboard. And I was like, what happened in that time? So the only thing that happened is that they enabled shadow traffic, and that brought up a lot of issues. And we had a strict deadline to make this work because of some internal reasons. Like we had to get it running by worst case March end. So we had to make it work hook or crook. So, but the issue was that it wasn't just queries. Like there was something going on with ingestion as well at that point, which we didn't know. So we had to start looking at our cluster and everything. And we had a really large cluster, so debugging, thread dumps, heap dumps, what have you. Like, and yeah, the master is like progressing 50 commits a week. So that was the problem statement at that point, and I think everyone was questioning whether Pino is going to work or not. I was also questioning it. I think if you were to like make people bet their money against it, I'm pretty sure everyone would bet it won't work out. But obviously, fine, it did. I'm giving the talk. So yeah, so we started by looking at. So I think there were like a lot of issues happening. So when there are a lot of issues happening, it becomes very hard to focus on what is exactly causing the issue, because if your server is crashing every 2 hours, like where do I start looking at even? Like so, the first thing we looked at was that the memory was going up even if I was like running 2-3 queries, or something like that, which suggested that there is something, queries are doing something which they're not supposed to do. Looking at the query, then we figured out that projection pushdown was not happening. So by projection pushdown, like in case you're not aware, like that essentially means that when you run a query like this one, like we have select count star from riders and so on and so forth. For the riders table, you need to do an index lookup on is online and country. And you need to read the user UIDs to do the join between the audiences table. But you don't need to read any other column. And the issue was that we had 100 other columns apart from these. So projection pushdown not happening means that we were reading all the columns. And this was a bug in like how we had wired the calcite optimizer and the SQL to rel converter. I worked with StarTree folks, and we figured out a fix for this, and thanks to StarTree like for merging it.
How did you root cause this? Like this is the issue, like you are reading extra columns also and this is not happening.
Yeah, that's a good question, and I appreciate that you understand that it was a bit hard to figure out. But I think I ran a bunch of, so for every query I was running explain plans, so that was one thing. The other thing was that we had two regions like most people do, and we asked our users like run your shadow traffic in the other region. I'll use the other region as my test bed for everything, and I was running queries, explain plans, thread dumps, and I think it was in a thread dump I realized that there is a lot of time being spent in converting the columnar data to row-based data, and that's where I figured out that this is probably happening. But that's a good question, yeah. So yeah, I think this was an issue in like how we were using the optimizer rules. This was a desperate time to the point I think there was a Pino issue as well, where I was having a discussion with Rong, and we were trying to figure out, at least I was trying to figure it out by asking ChatGPT, which is what you do in 2023. And it didn't help, just so, yeah, it was throwing us in like different directions altogether. So I think the approach that helped was like just download the Apache calcite code, look at every class and see like where the issue. I think this is like a startup opportunity if anyone is interested, but I think you have a code base, but it's very hard to figure out what solves your problem. It was just a single config in the end, but like figuring out like that it was a single config, especially for a complex system like calcite, was a hard thing that you have to go back and like once you know it, like it's obvious, but it's hard to discover it the first time. So that was something that we found out, and we found out like the fix for this. Like I think we can skip that. So yeah, that fixed the projection pushdown. The next thing we noticed was a lot of time was actually being spent by the scheduler. So the previous approach that the previous implementation of the scheduler was doing was it was trying to compute what are my next stages I can run, what are the next plan fragments I can run dynamically and synchronously. So, and that was very costly the way it was designed. So we rewired it a bit. We introduced some clean states about like in what states a given plan fragment can exist in. And we came up with a simple algorithm which was very efficient and which worked out for our clusters as well. And I think it's still that way. We have added like one more state to this to indicate the killed state. But other than that, it's pretty much the same. And yeah, the way it works is that it's a cooperative query scheduler. So as you might imagine, for a multi-stage query, you have different stages. Each stage will have its own operator chain, as we call it. So it's a set of operators that you run. And these are run in parallel, but most of the time, let's say your leaf stage is very costly, then your join stage or the non-leaf stages won't get any data. So they don't need to like occupy any thread or anything like that. They should yield the resources and let the other chains which are ready to take over and get scheduled. So that's what the cooperative query scheduler is. Like we have a state to indicate that a operator chain is available to run, but it doesn't have anything to run, which is the available state. The ready state is that you can just start running the operator chain right now. And the running state is when the operator chain is running and occupying a thread and consuming CPU resources and actually doing some work. So yeah, I won't get into the details of it, but like yeah, this also like got us a lot closer to. At that time, I was hoping for like even 90% reliability. For me is like an achievement, but we were hoping for 95% reliability. But this alone didn't get us there. We further found out that predicate pushdown wasn't working. For this one, the issue was that essentially, again, it was a calcite wiring issue. So how you configure your optimizer rules to run was a bit different than what it needed to be. And to explain this with an example, let's say you have a query plan on the left. In calcite, you have rules which look like filter project transpose, filter into joins, which essentially look at two rel nodes, which are the two relational nodes. And they'll compare their properties and they'll try to do push down, or they'll try to do merge them, or they'll do what have you. So that's how calcite rules are usually. But we were surprised is that how is predicate pushdown not working, because it is supposed to work. Every database is doing it, so something must be going wrong in our implementation. And what we found out was that essentially we were giving, so CalStat has a heuristic planner which we use. There's also a Volcano planner which is like a cost-based planner, but as far as I know, I think only Flink is using it, no one else is using it. But yeah, the heuristic planner essentially asks you to give it a set of instructions. And the planner essentially runs a program which will run those instructions one by one. And the issue was that either you could give all the rules as a single instruction, or you could give each rule as a separate instruction. And what we were doing was the latter when we found this issue. And what we needed to do was give all these rules in a rule collection so that they are run in a single instruction. Because if you run all of the rules in a separate instruction, what could happen is, let's say your filter project transpose rule is first, which essentially swaps the filter and project nodes. So it will push down a filter node past a project node. And your filter into join comes after that, so it pushes filter past join. Then if you have a plan like this on the left, which is a very common thing for anti-join queries, or like anti-semi-join queries, aka the not in clause. So in that case, this won't work because your filter project transpose won't be able to push down the red filter node, and your filter into join node will work, but you want the filter node to go down to the leaf stage. So yeah, that was the issue. So once you like run this in a single instruction, then the way the graph planner works in HEP program, like that takes care of like ensuring that all the rules are run together. So if one rule matches in one iteration and then second iteration the other rule matches, both of them will be run, and there is no specific ordering that you need to give them. So that was another good learning out of this. And yeah, finally I think we found that there were like a bunch of leaks happening in the system. There was like a bunch of reasons for this. I don't think it makes sense to go into the details of those, but at a high level what was going on is we have a kind of a Volcano style execution. So each operator is calling get next block within a stage, but across stages there is a push based mechanism. So for example, let's say you have a simple join query which has two child stages. The stages will run, since they're leaf stages, they'll start running immediately once you submit the query. But the join stage will yield and it will wait for the leaf stage to signal that there is some data ready. So once the leaf stage signals, okay, I have processed some data, there is a new data block coming in, the operator chain corresponding to the join node will like wake up and it will start executing, and it will start pulling data from, not pulling data, it will start consuming the data that is already pushed by the leaf stages. So it's a hybrid of like pull and push based. So in case like you're interested, like you can read the Volcano paper, but there is also morsel based execution that DuckDB uses. That is also interesting, but it is not something that we use. And I think that as far as I know, it's a bit tricky to implement in shuffle based and distributed scenarios. Like DuckDB is like single node, as you might know already. And some other things that made it a bit more challenging than like your general problem statements is that we had like gRPC versus local data transfers, which have different semantics. For example, like gRPC transfer will be done through a connection, and the connection, the server doesn't have any control over it. Like someone else is sending me data. I can like start saying, okay, I'll add a handshake and I'll reject things and whatnot. When failure scenarios, even the receiver might not even know that there is a query like this coming in. For example, like it could be that my query is running on 4 servers, and the dispatch to one of the servers failed, and that server is now waiting for data from the other servers, and the other servers are waiting for data from that server, and they could like and continue to like hold resources for the entire query duration. So there's like nuances there which like make this like a bit more complex to fix. And the other thing that made it complex was that at that time like we had a lot of push to go to higher reliability, so we were trying to like move fast, and our cluster was really big. So I had to deploy like over the night. In the morning, I'll see whether my patch is working or not, because the shadow traffic is like continuously running. But that's where the iterations also took a bit longer than they needed to, because this was only happening in cases where you have failures, where one client is failing out. You could say that you can implement this on a local level, which I definitely agree with. But essentially, you need time to do this, which we didn't have. So yeah, that was also complex, but yeah, that is also fixed now. And yeah, so the next step was, there were a bunch of other fixes, but that pretty much got us to 95% kind of reliability. The next step was going from 95 to 100. So this was back in March, we were around 95%. And finally, people were like, okay, this is maybe going to work out. We have to look at the last 5%. And we started looking into the other issues. Then we found out that our scheduler uses request ID, which is sent to us by the broker. And the request ID is a long integer, long, which is incremented from 0. So obviously, like if we have multiple brokers, then they'll collide at some point. And when they were colliding, we were seeing like all sorts of funny issues. So it was throwing me into different directions. We were seeing like things like, okay, schema is not compatible between stages. I was like, this is definitely a calcite bug. I spent a day or a couple of days like trying to see like this should be a calcite bug. I should be able to fix it. The funny thing was that when I ran explain queries and other things, like I wasn't seeing any differences, but somehow it was happening at that point. And another issue was that for this cluster in particular, we didn't have log aggregation enabled. So, and the number of logs is just too much. Like where do you start even looking at it? So yeah, we finally figured out that it's because of these collisions, and we made a fix for this. This is also fixed in V1 now. V1 also uses the unique request ID. So yeah, this also fixed a bunch of issues. And this is an interesting one, especially if you are in DB research or anything like that. So essentially, for the partial upset feature, which Uber itself contributed, we get the requirement there is that you have a table, and again, let's say you have a Kafka topic. You don't have the full attributes every time. You have like only one or like a subset of them, and you want only those to like act like an update statement in general SQL. So the issue with this is that when you are applying the updates, like you have to read the previous row, which doesn't match with Pino's columnar storage. Because if let's say I get one ingestion event which has 100 different columns, and I have to read the previous record, then I have to read like 100 columns, and the data is in columnar format, so I'm doing random reads on it. This doesn't play well with mmap, which is what we use. And these are like known kind of issues. Like Postgres also has this issue, but Postgres has the advantage that it is row based. So it doesn't like suffer as badly as this, but we did suffer a lot because of this. And the fix for this was something I think is a very ingenious kind of solution, which is we essentially like auto restart servers every 2 days. Yeah, so there's a saying, right? We're not shipping fast enough, you're not auto restarting or restarting your clusters every few days. But yeah, initially I was doing it manually, so I had an alarm clock in my phone to wake me up every 2 days or so at a given particular time. I'll click on restart on my UI, and that's how things were going. Then I implemented the auto restart. Meanwhile, I looked into like other solutions as well, and there are some solutions to this which I won't get into right now.
So why is high TLB shootdown also a problem over here? I think that's like at the micro level, but it would be a bigger problem because you're reading like n number of rows for all those columns.
Yeah.
So will that have an impact?
Yeah, so the issue is that your CPU basically becomes useless because we are having like 200k messages per second ingested across a bunch of servers, which is without replication. With replication, it's like 400,000. Each record has like 100 plus columns. So, which means that we are doing like millions of random reads. And after a certain point, most likely because of memory fragmentation, this issue becomes really worse. Like if you let the server run for a couple of days, initially in the beginning everything would work fine, but after a couple of days or 3 days, like it will start having issues. And that's why we had to implement auto restart. So going back to the TLB shootdown issue, the issue with that is that it basically renders the CPU useless because our CPU utilization is going down to 10% or so. and this was like astronomically high. Like the TLB shoot down, I think they were happening like for every memory access, because as you may imagine, like whenever a query comes in, as Chinmay also mentioned that let's say it has filters on 3 columns, you'll have to read those 3 indexes across a bunch of segments. And if each access is causing you a major page fault, that is like a lot of page faults. So, and this becomes worse with like NUMA systems which have like high number of CPUs. So it essentially didn't align with like our expectations and design in the end. So that is something we fixed with auto restarts for now. But I think generally speaking, you shouldn't have this issue, because I think the issue with us was that we were running it at very, very high scale, which is not very normal. I think normally things should be fine. We actually had been running partial upstart for a while in production, I think for around 8 months or so, for I think 10 or 5 different use cases. Going back to, I think why we did this. So I think back when from January, I think in May we rolled out to production completely. By May end, I think we stopped writing to the proprietary database. In June, the license is expiring for the proprietary database, so I think we're finally free and we have completely migrated. There's a lot of celebration as well within the team, especially from the customers team. They also spent a lot of time and resources on this. So it was definitely a collaborative effort there. And StarTree, I think I would also like to thank here, because they were also helpful in like working on solutions on most of the problems that I mentioned just now. So our latency expectation, so it depended on the queries, because in some users are looking for like 100 UUIDs, some are looking for billion UUIDs. So the latencies could vary from like 1 second to minutes. And in our case, like we did see a significant improvement when moving from that proprietary system to this system. And we also had a very big reliability improvement. So we had like in Grafana, we had like really graphs running at the same time. So in Pinot, it will show the shadow traffic reliability, and in the other system, it would show the real reliability. And we were like outperforming consistently, and which was a surprise even to the customer team. I think they were surprised how fast Pinot is, which is something good. But yeah, we had like around somewhere around 99%. So this 99% is coming because the queries are dynamic. So unlike most analytical use cases, your data process is like interactive in a way. So it's more closer to interactive analytics as opposed to real-time generally when we talk about real-time analytics in Pinot. And I think the last thing I'll just touch upon is the technology consolidation, because that is a really underlooked maybe still. I think we keep on calling it out, but it's still very underlooked, because in a company, if let's say you have 5 different systems, you need 5 different support teams, you need 5 different types of expertise. But having just one like really reduces your costs long term. And I think Pino is really helping us out there. And yeah, and just to close, we are adding some support. Some of the things we are still POCing, but I think hopefully you should see more PRs in H2. And yeah, that's pretty much what I had. If there's still any questions.
Thanks, Ankit. Next, I'm going to talk about the TTL support for Pinot Abstract. And welcome to my talk. Yeah. So I'm Qiao Zhu. I'm from the Uber real-time analytics team at Uber. So today I'm going to cover the following topic: the overview of Pinot Abstract, and then I will talk about what are the challenges we met when we onboard some of the use cases, and then I will talk about this feature to memory to improve the Abstract memory usage, and then we'll talk some of the benchmarking result and also talk about some future work. Yeah, a bit about myself. I'm a software engineer at Uber, and I'm majorly focusing on the Pinot features and the real-time analytics ecosystem. So I'm the contributor for the partial Abstract and Abstract TTL. And next part, I want to talk about Pinot Abstract. So Pinot is the first ever OLAP that has the Abstract feature support. And also, Uber contributes this feature to open source. And in the following section, I'm going to talk about why we need Abstract, what is Abstract, and some of the Abstract use cases at Uber, and then the Abstract architecture, comparing full Abstract with the partial Abstract. So let's take a look at this example. This is a very interesting example from the ads data flow. As you can see from here, we have get this impression, click, and orders signals from the Uber Eats app. and then pre-process through this Apache Flink. And then the data will ingest into Pinot to power this pacing, building, and also analytic metrics. And the requirement of the customers, they want this data set to be fast, reliable, and accurate. The fast means that they want this data metric to be powered in the real time. And reliable means that they do not want the data loss, so that there will be revenue loss. And the last but not least, the exactly events feature. They require this feature because we do not want to overcharge the customer or double count. So how this come up with the requirement for the abstract. So the user wants the data to be there updated and corrected in the real time. And Pinot should deliver this updated fresh data view to the customer. And also the user still want to use some SQL to query the Pinot. But as we know, there's no like SQL equivalent in the Pinot that can represent the abstract functionality, which means that the real-time update of existing record. So it's proposed and designed the abstract feature. Yeah. So there are like a lot of abstract use cases at Uber. I think Ujjwala already covered them. Majorly there are 3 categories, like actionable insight, and also this real-time decision, low latent, time-sensitive decisions, and also the improve the customer engagement. So I'm going to talk about the architecture and skip this slide. Thank you. So for the full abstract, this is introduced in the Pinot 0.6. So as we know, the real-time data are grouped in the segments, and segments are actually distributed on different servers. And this server, one segment might have multiple different replicas, right? So we can avoid we can query in the parallel and avoid the bottleneck of the single server. However, this brings some of the challenge for the abstract because when you do abstract, you want to find the record that's sharing the same primary key. And to find out that if this primary keys that are distributed to the multiple servers, you will be finding this as a challenging problem. How are we going to solve that? We propose this local key coordinator approach. And so each of which guarantees that each of the primary key will be partitioned, pre-partitioned in the source topic and get into the same partition so that we can look up the previous record with the same primary key efficiently. So let's take a look at this architecture. We have like multiple components for the Pinot Abstract. So first we have this Abstract local key coordinator to keep track of the primary key to record location mapping. And second, we have this valid doc index that on the segments level to keep track of the record that is valid. For example, your most recent record should be marked as a valid record, and the previous record that's sharing the same primary key are marked as invalid. So when your query was executed, you will be able to filter out these valid records. And next, we have this stream ingester that will be able to update these 2 metadata that I mentioned before. One is the abstract index, another primary key index, another is the valid doc index. And last but not least is that we have this query broker to dispatch this query to, for the same partition to the same server, so that we are able to provide one consistent data view. So we leverage the partition by key feature in the Kafka to pre-partition the source topic. So there's another set of use case that is called partial abstract. Let's think about an example. So for Uber, we have some of the trips, and we want to keep some of the field, which is the trips metadata. But we also want to update some other field, like driver files and or driver status. So what can we do that? We propose this kind of requirement. We want to specify some field to be updated, while the other field we want to ignore and keep them as it is. So how are we going to do that? We are supporting this partial abstract feature. So when we do the injection, we propose different, we are utilize a partial abstract handler inside this real-time data manager. And in this data real-time handler, we are trying to look up the previous record. And within this record, we are applying the update to this previous record and get the full update and index that record. So that is another like design alternative is that we can also try to merge the result when we query. However, that will be less performant during the query time. So we select this approach to perform the merge during the injection. And also this is supporting a rich set of different merger strategy at the column level and table level. You can define on which column you want to apply this override, on which column you want to apply this ignore, which column you want to increment the file to the previous file. So these are, there's a wiki that we can take a look. Yeah. So that covers the overview of the upsert. So in next section, I will talk about some of the upsert optimizations and what are the possible issues that we encounter during onboarding these upsert use cases. The first thing is that sometimes when we onboard a upsert use case, if the table is large, we observe that the memory usage on these upsert servers are relatively higher than other servers. So this is because we are storing two kind of index in the memory in the heap. So we want to first take a look at the in-memory metadata, and then we want to talk about what are the improvement, how can we improve the memory usage. And then we will talk about what is the upsert TTL feature. It's one of the solutions to improve this memory usage. And last but not least, if we have time, we will cover some of the data consistency issue we met with the upsert TTL when we implement this feature and how is it resolve it. So let's take a look at the memory metadata. As you can see, this is a one partition. There's segments sealed and segments mutable. You can see if there's no record that is duplicated, all these primary keys will be stored in this primary key index, right? And on the segment side, on the segment level, you have this valid dog ID that keep track of the valid dogs. And if there's another new record in this mutable segment, consuming segments, and it's sharing the same primary key in the same partition, we are able to find out this primary key in the upsert primary key index. And then we update this primary index, the record location. And also we mark the previous valid doc ID, that's a doc ID as invalid record, invalidates that record. So this is how the memory data structure looks like. And if your table is large, you have to keep all these kind of primary keys indexed in your memory. So how do we improve the memory usage, and how are we support this upsert use case efficiently? I think there are multiple guidance or this best practice. The first one, you can follow this best practice on the open source wiki. So basically, we have several suggestions. First thing, you can pre-partition your source topic as many as possible, so that you can leverage more hosts to store your primary keys, so that each of it will not easily to hit the bottleneck of a single host. And second is that we can also try to avoid using a composite or complex primary key. We can try to use this single primary key, simple data type primary keys. But what if this is a requirement from the business that you have to use a composite primary key? So there's another feature that contributed by Uber. It's called a hash function. So this hash function on the upsert config can help you to do a hash to your primary key, and you can only store 128 bits of your hash code of your primary key size. Even though there is a possibility that it's very low possibility to get this correlation, but still it will improve your memory usage a lot for the key space. Another interesting feature that we also want to talk about is the dedupe feature. So dedupe feature is actually contributed by StarTree. Since this is a feature that so for some specific use case, they do not care what is the most recent record. So they can just ignore the subsequent record after the first one. So in that case, they do not need to keep track of all the record location in the memory. They only need to keep track of the primary keys. And furthermore, we can also move the upsert metadata off heap. There's a patch from Uber that is aiding the persist data storage called the RuxDB plugin, so that we can move some of the metadata off heap. And last but not least is the live session for primary key. So this is the pre-request for use case that we want to use the TTL to reduce the memory usage. So what does this live session mean? The live session means usually for a specific set of use case, the primary keys will only get frequently updated during a smaller time window. So you do not need to keep all the primary, and also after this time window, your primary key will not be updated anymore. So with that, you do not need to always keep your primary key in memory during your rotation of your table. So we can take a look at this graph. So as you can see from here, the table rotation can be relatively long. For example, 7 days, 30 days, 90 days. But you can specify a metadata TTL, which keep track of your primary keys. And if after this metadata TTL, your primary key will get expired, and we will remove it from the memory. And that will, because this primary key will not be updated, which means you do not need to keep track of this record location. There are two requirements for this feature. The first requirement is that the out of TTL primary keys should be removed from the heap so that we can save the memory. And the second thing is that the valid dog index on the segment side, this should still be there. This should still be maintained, and this should not be removed. But it's very common that we always, like sometimes we restart server, shut down server, replace host, right? So when that happens, we have to rebuild this in-memory data structure. And as we know, the valid dog ID is actually derived from the primary key index, because you basically you are trying to see each of the entry and mark when you add a new segment, you build this valid dog ID every time, and you try to see if this record is valid or not, comparing the comparison time with the existing after metadata. But in that case, if you apply the TTL, your primary key index already been like remove this old primary key from this primary key index. And in that case, you cannot derive your valid dog ID. So how can we do that? So we propose this valid dog index snapshot so that we can persist this snapshot during this segment commit. And with this segment commit, we will be able to persist this in the local host. And next time when you adding this segment back, you will be able to get your valid dog index from this valid dog snapshot. And also we propose another thing called largest in TS watermark. So the Pinot Abstract by default is using the time column value as the comparison column to determine the order of the message. So, and also we want to know which one is the latest record and using that as the valid dog, right? But you can also specify something called comparison column in your Abstract config and using that value to mark or determine which record is the latest one and valid. So we keep track of this TS watermark value, and also we persist it every time when we remove the primary keys from the primary key index. So that next time when you restart server, you still does not lose track of your largest in TS value. And with this TS value managed by the TTL, then we get to know what is the time that the primary key is expired and what are the primary keys that can be removed from the primary key index. Let's take a look at an example. So as we can see, there are three categories or three types of segments: consuming segments, seal segments, and out of TTL segments. So the seal segments and out of TTL segments, these are immutable. And consuming segment is the one that we still can be discarded, right? So as you can see from here, if the first segment get inside the Pinot table, we see it introduced 3 new primary keys, and this was stored in the primary key index. And when we ingest, after the segment 0 was getting sealed, we have another segment. In the new segment, you introduce some other primary keys, and it might invalidate the previous primary key, like a doc ID in the previous segment, and it will also be adding to the primary key index. And next step, we have this segment 2. And as you can see from here, this segment 0 is already out of TTL, but it's still in the rotation. Since it's still in the rotation, the valid doc ID should still be there. But this primary key index, this will be updated, and previous doc ID primary key will be removed from the primary key index. And yeah, so this graph majorly talk about, as you can see from here, the primary key index was purged, the out of TTL primary keys, but the valid doc ID are still there. Yeah. So these are POSIX codes that I'm not going to cover in detail, but I want to let you know that these are there's a PR that talk about this code. And these are functions that we support, like we remove the expired primary keys, and also we know how to add the segments with TTL. If it's out of it's already out of TTL, is expired, we should not add this primary key to the metadata. Otherwise, it might be overload this server. And when we recover the valid dog index, previously we tried to leverage the primary key index to derive it, but now we just get it from the snapshot. Yeah. So now I think we want to cover some of the most interesting part, which is when and where should we, when and how should we persist snapshot, take the snapshot, and also purchase the primary keys, and also load or update persist the watermark. So the first one, actually, in the first version of implementation, we are taking a snapshot during the segment removal. And during the segment removal, we always make sure this snapshot is persisted with the most reflects the most recent data. For example, you have a consuming segment that might invalidate some of the existing docs in your sealed segments. However, when the segment was removed was called, you will see that this invalidated doc IDs are also being persisted into the snapshot. However, when you restart server at this time, the consuming segment will be discarded, and but your snapshot is already commit this invalidated primary keys, which means when next time you start the consuming, before you start consuming the new segment, you will be losing, or there will be some data inconsistent issue. So the data like persist the snapshot during segment removal is not a good approach. So thanks to the like collaboration and comment from open source, we have moved this to before the new segment start consuming. So with that, every time there's new segment start consuming, we will be taking this snapshot and also remove the primary key synchronously. And this TS watermark is something that is largest timestamp that we see. It shouldn't be the Kafka time or the message time. It should be the event time. So this value should be coming from the ZK metadata, which is a comparison value from that column. Yeah, next part. So I'm going to talk about some of the experiments that we run at Uber and also what are the production timelines and future works. So we have done this kind of test internally, and also we draw this to an internal cluster and build some of the POC use cases. We have verified the memory usage and also verified restart the server. This injection should not stop. It shouldn't get into some like a deadlock issue, or it shouldn't have some like data consistent issue. And last but not least, we also verified this compatibility when we disable or enable this absurd metadata, absurd TTL in the config, and we restart server. The TTL will be able to pick up. So as you can see from here, so we enabled this absurd TTL during like 5:30. I think at that time we give it a very aggressive value, as you can see from here. So the memory usage has dropping a lot, and then we can also enable it, re-enable it, and restart the server. So restart the server means that we are rebuilding or rebootstrap the data manager and pick up this new config, and then this usage is coming up. So we can do this without dropping and recreate the table. Yeah. So the production timeline at Uber is that we have do this code complete in Q2. I think the diff is approved. There's some like minor comment that we have to resolve before merging this into the master, but I think I'm working on that. And next part is that we have on board some POC use case in some cluster. And yeah, so in Q3, we want to roll out this feature to the prod and also apply this config to some of the use case that is suitable to adopt this feature. For example, we have some use case that like trips. So there's like each of the trip events, they have like several states like start, pick up, drop off, complete, right? So these trips may only like last for 1 day. However, the user may want to have a view of like last 30 days trips data. So they may create a table with 30-day rotation and with a TTL of 1 day. So these are like one use case that we can adopt. And for the future work, there are two future works that we are going to work on. One is the deep store integration. So the current snapshot and watermark are only persist in the local host. The reason why there's a challenge to persist in the deep store is that this watermark and also the snapshot are actually at a partition level. So which means each different partition may have like different watermarks or the snapshot. So we want to have a discussion with open source and see how can we support this in deep store. Another thing is that, as we mentioned before, there's also a dedupe feature. And this TTL is not applied on dedupe feature at this moment. So we also want to contribute this to the open source. Yeah. I think also this is like a collaborative work from Uber and StarTree. I also really special thanks to reviewers and community support like Yupeng, Ting, and Jackie. I think that covers all the